All right, guys. Hey, so we're going to begin discussing our nuclear chemistry, right? That's our next chapter. So with some things to have kind of out and ready here, in this case, would be your periodic table, your notebook or notebook paper, whatever you generally take notes in. And not that a calculator is super necessary, but it might come in handy from time to time. So if you need to, just go ahead and pause, get those things out and ready so we can get going, okay? As I mentioned, we're going to be doing an intro to nuclear chemistry. So there is some differentiation in terms I want to discuss here real fast. So isotope versus radioisotope. So in this case, we're talking about a radioisotope being something that is not stable, right? So isotopes, if you recall, are just the different versions of the same atom, right? And essentially, you just have a different number of neutrons. So some configurations, though, are not stable. So our radioisotopes are referring to those types that aren't stable, right? So these unstable configurations are referred to as radioactive, hence the term radioisotope. And they have that unstable nucleus, all right? But what's important to us in this case is they will undergo what we call radioactive decay, all right, until it reaches that stable configuration. And just by the way, when I say configuration, we're usually referring to some sort of proton to neutron ratio. And that takes us back to that band of stability exercise that we're working on right now, which we will bring back in this week just to kind of tie some things together. All right. So radioactive decay is when the nucleus, so this is when the nucleus undergoes changes. All right. And that can look like lots of different things, right? It can cause an increase in the number of protons. It can increase the number of neutrons. Or it can just decrease the overall size of the nucleus. And we're going to talk about each of those three processes kind of individually as we go. All right. So electron emission is the first type of radiation we're going to talk about. All right, often referred to as beta decay. So electron emission or beta decay. One thing I want you to think of first is a neutron, right, is essentially a proton and an electron that have been fused together. All right. So a couple of things to remember from last chapter. So our nucleus is composed of protons and neutrons, right? A neutron, though, essentially is if you take a proton and an electron and fuse them together into one, the charges cancel, so we get zero charge or a neutral charge. But the mass remains more or less constant because electrons essentially have no mass. They do have some, but it's really not very significant in that process. That's why we say a proton and a neutron have essentially the same mass. It's because even though a proton's been combined with an electron to make a neutron, the electron is so small that it really has no appreciable change in mass there. All right. So when a nucleus is deficient in protons, we often refer to that as a neutron-rich nucleus. All right. What can happen is if that's not stable, in this case, a neutron transforms into a proton, and it's done that by shedding an electron. Okay, so that's why we call this electron emission, right? Electron emission is that process of shedding an electron. All right, so what we see happen as a result is an increase in number of protons, right? So our number of protons goes up +1 for each emission, okay? A decrease in neutrons, -1. But we get no change in mass. Again, we're emitting an electron from a neutron, making it become a proton again. Okay? So again, a neutron is a proton and electron combined. If there's too many neutrons in the nucleus, one of those neutrons can shed an electron, right, to become a proton. So our number of protons goes up, our number of neutrons goes down, but because electrons have essentially no mass, when we get rid of that electron, the mass stays constant. All right. So in the case of helium-6 and lithium-6, so helium-6 would look like this: He, 2 protons, and a mass of 6, right? And that would have 4 neutrons, 2 protons. So that ratio for helium, 2 to 1, doesn't really work out very well. There's twice as many neutrons and protons. It's an unstable configuration. All right. So we have too many neutrons. So we're going to undergo this electron emission. So one of these neutrons is going to become a proton by shedding one electron, right? So in this case, we're going to increase the number of protons, so that means that 2 is going to become a 3. My mass, okay, is going to stay constant, so that remains 6. All right. Now, because I now have 3 protons, remember we talked about protons are those identifying particle. If I have 3 protons, I am not helium anymore. I am now lithium, right, with 3 protons and a mass of 6. And if you look at the periodic table, you'll see that most lithium atoms have a mass of 6, which tells us that lithium is most likely stable, with that mass at least, is a stable version. All right? So we had an unstable version of helium. We underwent this electron emission, a radioactive decay, to change our nucleus configuration so that we now have 3 protons and 3 neutrons, right? Which is a 1-to-1 ratio, which for our smaller elements works out great. So that's electron emission. All right? Now, the other type we can have is we call positron emission or electron capture. Now, both these are different processes, okay, but they have the same result, essentially. They just kind of happen under different conditions. So there are 2 different things that can happen to cause the same thing. All right. So positron emission or electron capture happens when, rather than having too many neutrons, right, it's deficient in neutrons, or it's got too many protons in this case. So our proton to neutron ratio is off, but in this case, we don't have enough neutrons to make us stable. All right. So when a proton sheds a positron, so you can take a proton in this case. Now the particle that makes the proton positive is what we call a positron, and a proton can essentially get rid of that. Again, reducing its overall charge to 0. A positron, like an electron, has essentially 0 mass, right? So that proton loses a positron, it becomes neutral rather than having that positive charge, but the mass stays the same, all right? Or we can capture an electron. So if we have a smaller atom, we're usually going to get rid of a positron. If we have a bigger atom, we're usually going to capture an electron. Okay? So lighter ones shed a positron, heavier ones capture an electron. Okay, but what you have to remember is the result of this is essentially the same. Okay? In both cases, we decrease protons, right? So our atomic number goes down 1. We get an increase in the number of neutrons. It goes up 1, right? Now, losing 1 proton, gaining 1 neutron, but in either case, no change in mass. All right? So some examples we can look at. We have magnesium-23 transforming into sodium-23, right? And krypton-81 transforming into bromine-81. In both cases, we're decreasing our atomic number. Okay? We're increasing the number of neutrons, but notice the masses remain constant. All right, so let's look at each of these a little bit more carefully. So we have magnesium-23 in this first example, right? So we have Mg. So its mass is 23. Now, all magnesium have an atomic number of 12, right? So in this case, right, for magnesium-12, we're going to have 12 protons and 11 neutrons, right? 23 minus 12 is 11. Okay, so that ratio doesn't really work out as a stable configuration. So this is our radioisotope, right? Magnesium-23 is radioactive. That ratio of protons and neutrons is not a good stable configuration for magnesium. Okay, so it's going to change. Now in this case, though, we're deficient in neutrons. We have fewer neutrons than protons, so we have too many protons. So what we can do is magnesium-23 being one of our lighter elements, so the elements farther up the periodic table would be our lighter, right? So we're probably going to shed a positron in that case. So we're going to take one of my protons and turn it into a neutron. So essentially, okay, rather than having 12 protons, okay, I'm going to have 11 protons. Now what that does for me is that makes a 1-to-1 ratio. 11 protons, actually, and 12 neutrons. So it's not quite a 1-to-1 ratio, but generally in our ratios we like to have maybe a little bit more neutrons, but we'll get to that later. Okay, so my new ratio there is, but because I have 11 protons, I am no longer magnesium, right? So my notation would be 11 23. So still have a mass of 23. That remains constant. My atomic number goes down 1. But the element that has 11 protons is not magnesium. It is sodium. All right? So that would be what I transform to in that case. Right? So magnesium being a lighter on the top side of that periodic table, lighter element, we shed a positron. Now, if I look at krypton and bromine, I'm getting up on the periodic table a little ways. It's a heavier element. Right? So krypton 81 has a mass of 81, and it has 36 as its proton number, right? Now, heavier elements need more neutrons, all right? So in this case, I would have 36 protons, and 81 minus 6, this is why the calculator might come in handy. 5, 7, and 45 neutrons. All right, so if I add those two numbers up, I get 81. All right, so we're still saying this is deficient in the number of neutrons. All right, so this ratio, 36 protons to 45 neutrons, is not stable for krypton. Okay, so what am I going to do in this case? We're still saying that we are deficient in neutrons, so I'm going to turn one proton into one neutron. All right, so I'm going to decrease my protons by 1, so I'm going to end up with an atomic number of 35. My mass is going to remain 81 because a proton turns into a neutron, but because my atomic number is 35 now, I am now bromine. All right. In that case, though, we captured an electron to cause that to happen, and that's what happens with our bigger elements. All right. Now, last but not least, we have an atomic number above 83. So if you look at the periodic table, you find number 83 on your periodic table, you'll see that that's bismuth, right? Anything above bismuth on the periodic table is essentially not stable. It might take a really long time to decay. It may not be particularly unstable, but the nucleus is just too big in that case, all right? So too many protons and too many neutrons, right? So we actually just get rid of chunks of our nucleus, and that's what we call our alpha particles. Right? So when our nucleus is too big, we emit alpha particles, and that's essentially a helium nucleus. Right? So if we're getting rid of an entire helium nucleus, this is what our result is. We decrease 2 protons, so minus 2 in our atomic number. Decrease 2 neutrons. So because we're actually getting rid of both protons and neutrons, right? 2 protons and 2 neutrons, we decrease 4. Okay, so our mass actually goes down by a factor of 4. So keep in mind with our beta decay and our positron emission / electron capture, our mass stays constant. With alpha decay, so again, that's with big elements, we actually decrease our mass by 4. All right, so an example here would be radium-222, which is radioactive, becoming radon-218. All right, so radium-222 would look like this, 222. All right, so radium-222, and it has an atomic number of 88. All right, so what's going to happen is this is just too big. The atomic number is 88. It's above 83 in that case, right? So it will undergo an alpha decay, and when it ejects that helium nucleus, okay, we're decreasing our mass by 4 and our atomic number by 2, right? So my atomic number is going to become 86. And my mass is going to become 218, right? So minus 4 for mass, minus 2 for our atomic number. And now, because we changed our atomic number, we actually have a different element, which is radon. Now, radon, if you'll see, notice, also has an atomic number above 83, so it would actually end up undergoing another alpha decay until it got down below that atomic number of 83. So we can undergo multiple decays, and we'll learn about that later. All right? So what I want you guys to do for your homework and classwork is we're going to do nuclear equations and how to write them, right? Textbook pages 242 through 246, and we will be working on ChemQuest number 84, which you guys will get in class. There's also a copy saved right here to Edmodo. All right? So if you're absent today, this is what this recorded lecture is for. All right?